Okay, so it's a pleasure to, oh, you really want this to start right away. So it's a pleasure to welcome today's speaker, Daniele Oriti from Universidad Complutense de Madrid. Daniele, has worked on for quite a number of years on many aspects of quantum gravity, especially emergence of space-time, and also interest in foundational aspects of quantum mechanics. He, among other things in his career, he was a group leader at the Albert Einstein Institute, the Max Planck Institute for Gravitational Physics, as a recipient of a Sophie Kovalevskaya Prize of the Alexander von Humboldt Foundation. And some years later, he was also at the Ludwig Maximilian University in Munich, also with a prestigious fellowship, the DPG Heisenberg Fellowship. And today he's going to, so it's a pleasure to have him here. I've known him for quite some time. I think we first met at the Albert Einstein Institute when I was a postdoc there, and you were just starting to lead that group, working on emergence of space-time in quantum gravity. And today, I think he's going to tell us about interesting aspects of information structure when studying quantum gravity and to study the emergence of space-time in that context. So, Daniele, the floor is yours.
Yeah, thank you so much for the introduction. I hope you hear me well. So thanks for the introduction and for the invitation to present some results and some ideas. So I state outright what the goal of this presentation is. I just want to illustrate how a number of quantum information structures and tools are relevant for quantum gravity models, in particular a certain class of them, in which indeed space-time is described as a sort of a peculiar quantum many-body system. And I will discuss both the structure of quantum states as well as the dynamical processes for these quantum states. So let me start with a little bit of motivation and context. I would emphasize that to appreciate what is going on in all these approaches, I think is useful to shift the perspective about what quantum gravity is supposed to be from the idea that quantum gravity is going to be obtained, is going to be the result of quantizing through whatever quantization algorithm the classical general relativity or some other gravitational theory, to a perspective in which quantum gravity is understood as simply, more generally as a quantum theory of some fundamental building blocks, some fundamental degree of freedom underlying space-time, geometry, fields, and gravity. So that all these notions have to be understood as emergent. Now, there are a number of motivations for that. It's not the point of the talk to convince you that this is the right perspective. And in fact, it's not entirely incompatible with the other one, with the more traditional one. But there are a number of motivations, a number of results in semi-classical physics that can be argued suggest that indeed you need some other fundamental structure than spatio-temporal fields living on some smooth manifold. Whether they are quantized or classical or whether they are quantized or remain classical. Now, in fact, suggestions in this direction come also from existing quantum gravity approaches, including those that start a little bit in a more traditional conservative manner with the purpose, with the goal of quantizing the classical theory. So there is I detect, let's put it like that, a convergence of ideas. And at the end of the day, it's simply an interesting perspective to pursue and to see how far we can go. So suppose that indeed space-time geometry fields are all non-fundamental. It means that there is some other type of structure, possibly discrete type of structure that underlies them. And gravity and geometry and space-time itself have to be understood as a sort of a collective phenomenon. Now, From this point of view, then almost by definition, if you preserve quantum mechanics in some form, then the universe is in fact understood as peculiar, because still background independent from the point of view of geometry and space-time, a peculiar quantum many-body system. So that's the perspective I'm going to use here to appreciate the results. And let me move on to tell you what the type of structures we're dealing with are. Before going there, still in this general introductory and motivating part, I give a couple of examples of approaches to quantum gravity that even if they start using at the beginning space-time structures, or they even start as I said, from the traditional perspective of quantizing the classical theory, end up with more fundamental structures that indeed are different than standard continuum manifolds in fields. This is the case, for example, for canonical quantum gravity that ends up working with the piecewise degenerate quantum geometries, or piecewise flat in some formulations quantum geometries, which are in fact geometries. Because all of this can be reconstructed differently from the fundamental theory depending on the approximation. And the idea CFT also gives a concrete example of the idea of emergent gravity, and at least emergent space for what concerns one dimension of space from a spatio-temporal theory on the boundary. Related to this idea of space-time emergence is the idea of the possibility of reconstructing geometry from entanglement. Now, there are a number of results, mostly again in a semi-classical context or in the idea CFT context, that show how this reconstruction could work. And they all have to do with computing quantum correlations in a standard field theory, normally in a CFT, and relating the quantum correlations to geometric properties of the underlying space-time. There are many of them. One of them is the Ryuta-Kanayagi entropy formula that we will encounter later on, although in a different context, and in which you compute the entanglement entropy between two regions on the boundary of ADS. And it turns out that this entropy goes with the area of some bulk extremal surface, separating the two regions in the appropriate sense. And all the idea here is that it's convenient and appropriate to switch the perspective. It's not that you have a geometry, a length, an area, and so on, and you define entanglement as a function of those. But it's a bit like that. You can try to define what you mean by an area and length and other geometric quantities. You can try to reconstruct them from measures of entanglement. Now, we would like to have a realization of this idea in full quantum gravity, and I would argue, maybe a bit provocatively, it's not a definite statement, but more of a suggestion, that in emergent space-time scenarios, this reconstruction of geometry from entanglement, from quantum correlations, is almost a necessity, in the sense that because by definition you don't start with geometric structures and you have to reconstruct them, and you're basically left only with some quantum degree of freedom related to some different type of non-geometric, non-spatio-temporal structures, is almost inevitable that it's quantum correlations that will be the key for reconstructing and defining geometry in some approximation. Anyway, let me go now to the a bit more technical part. In much of what follows, I will skip a number of details because of, well, limited time and because that's not the main point to kill you with mathematical details or specific steps in specific calculations. I want to convey the main ideas, but of course I'm happy to clarify some of the more technical steps. Okay, so the first point I want to get across is that in number of approaches to quantum gravity, the states of the theory underlying a quantum space take the form of entanglement networks of quantum geometry blocks that you can call pictorially atoms of space. So, in fact, in many such quantum gravity formalism, basically the type of structures you have is just algebraic data on a graph. And you can think of constructing these states by taking elementary Hilbert spaces associated to nodes, and then defining the connectivity of the graph in terms of entanglement across subsets of degrees of freedom associated to the different nodes. So there are a number of proposals for the concrete realization of the structure. I will discuss one in more detail, but again, emphasizing the shared aspects. So take as a fundamental Hilbert space, a minimal system, elementary system, a single block of discrete space. So a classical tetrahedron, so a little simplex which is flat inside. So you can embed it if you want in flat space, but at the end you only care about the intrinsic geometric data, and you don't care about the overall embedding because you don't want to rely on that embedding structure. So you can quantize the classical tetrahedron. So you can associate the classical phase space in which functions on the phase space will give geometric properties like lengths, areas, volumes, angles, and so on. And then you can quantize. The result of that, of course, I'm skipping a bunch of steps and many results, but the result of that is a Hilbert space in which a basis of states is given by an assignment of spins, so SU2 representations, to the faces, the four triangles of a tetrahedron, and they are intertwined by an invariant tensor, which also carries an additional label at the center of the tetrahedron. So in practice, you have a minimal Hilbert space, which is the tensor product of four representation spaces for SU2, constrained by requiring invariance under the action of SU2 over diagonally on the four representation spaces. That is what produces the intertwiner at the center. Now, if you know about canonical loop quantum gravity, for example, or spin form models and related, well, you realize that this is just a spin network vertex. It's just a node with four outgoing links corresponding to the four triangles labeled by spins. Now, there is a sense in which there are discrete geometric operators associated to the tetrahedron. You can compute in the classical theory the phase space function corresponding to the area of each triangle or to the volume of the tetrahedron itself in flat Euclidean geometry. And then you can quantize this by whatever quantization method you prefer. And you get operators acting on such states. And it turns out that you can diagonalize these operators. So you have a discrete spectrum for the area and the volume. Now, this is a common building block for a number of approaches. I want to just stress what is the overall picture here. Take this as the minimal building block, your single atom, and then consider a situation in which you have many of them. You have a sort of many-body system with the Hilbert space for each atom being the one I just described. In different quantum gravity formalism, then you have a slightly different definitions of the Hilbert space of many such tetrahedra, but this is the shared building block. Now, a single tetrahedron has no chance of representing, of allowing the reconstruction of any smooth geometry. At the very least, you should be able to take many of them and start correlating them, gluing them together. If you think of just lattice gravity, this is intuitively obvious. At the very least, you should be able to construct extended lattices. It turns out that if you want to start from the quantum building block I gave and glue different tetrahedra to form extended quantum simplicial lattices, what you have to do is to impose a maximal entanglement across the faces of the tetrahedron you want to glue. And maximal entanglement, therefore, across the subset of quantum degrees of freedom in the relevant Hilbert spaces associated to those faces. So you basically impose this maximal entanglement, and you can do it in many ways. An elegant way is to define, linking maps that do nothing else than tracing in the relevant Hilbert space over the SU2 data. And so if you want to reconstruct an extended lattice out of these quantum building blocks, you can tell me what is the adjacency matrix of the graph dual to that simplicial lattice, and just have this linking map for each non-vanishing entry of that adjacency matrix. So for every link of the dual graph you want to have. And then from a general product state of uncorrelated quantum tetrahedra, you can obtain a correlated entangled state that you can interpret as associated to a simplicial complex, which has a non-trivial connectivity. Now, this is a bit of the underlying idea, but what you end up with when you do that in this construction is in fact, the spin network states that are common to canonical loop quantum gravity, spin farm models, group field theories, and in fact, simplicial quantum gravity if you formulate it in terms of connection variables. So first order gravity, connection and tetrad. The spin network states are just that. So you have a graph that is dual to some simplicial complex made out of tetrahedra glued to one another. And in this graph, the links are labeled by representations of SU2 and the nodes with the intertwiners. In all these formalisms, you are allowed and in fact compelled to superpose graphs, so to superpose quantized discrete geometries. Now, already at this level, very minimal, and I'm starting really from the building blocks and building up, you can see some seeds, some primitive form of entanglement geometry correspondence. I told you that for individual tetrahedra, you can already have some notion of discrete geometry. But what is crucial is the next step I mentioned in the previous slide, which is that, in 2 slides ago, which is that the very adjacency relations in your lattice are nothing else than patterns of entanglement. So connectivity is in fact entanglement. But then you can also ask what is the entanglement across the shared triangle across 2 tetrahedra, and you can show that a measure of entanglement scales with, in fact, the dimension of the Hilbert space associated to that triangle scales with what becomes the area of that triangle. And similarly, the entanglement across the degrees of freedom on the 4 faces of a single tetrahedron scales with the volume of that tetrahedron as defined in the reconstructed simplicial geometry. So you have a very primitive form, but possibly more fundamental, of entanglement geometry correspondence. If you know about tensor networks, then you should have realized that the type of construction I gave, starting from the Hilbert spaces of quantized tetrahedra, is basically the one of projected entangled pair states, so PEPs, tensor networks. So in which you have Hilbert spaces of nodes, and you create, in fact, the resulting graph, the resulting network, by enforcing entanglement across the nodes. So because we have invariant tensors, we have a special class of tensor networks, which are symmetric tensor networks. On the other hand, normally we have some probability distribution coming from the dynamics or from the more general choices of quantum states for the assignment to the specific tensors on the nodes. And so we are in the class of random tensor networks. So on the other hand, we're restricting the tensor network formalism to work with symmetric ones under the action of the group we have chosen. In our case, it was SU2. On the other hand, we are very much generalizing the usual tensor networks. First of all, because we can have an arbitrary assignment of spin labels. That is, we can have an arbitrary assignment in the tensor network nomenclature of bond dimensions to the links. Moreover, as I said, we can superpose the assignment of labels to the links because these are our quantum degrees of freedom. So the typical state will be a linear combination of PEPs, tensor networks. Further, as I said, a general state in all these quantum gravity models includes a superposition over different networks, over different graphs, over different simplicial complexes. So we really have a further generalization of the tensor networks formalism. Okay, now I will have a few so a few slides on some more technical results we can obtain using this tensor network reformulation of quantum gravity states, in turn understood as quantum many-body states. And I'm staying at the kinematical level now. I'm not saying anything about the dynamics, which I will turn to later on. So suppose you have an open network, so an open spin network state, meaning you have a graph which has also some open links, in addition to more connected, closed structure. We can separate the type of degrees of freedom we have in this quantum state in two parts. A part corresponding to the spins and the magnetic numbers associated to the boundary links, and we call this boundary degrees of freedom. And then the remaining degrees of freedom, which are the spins associated to internal links and the intertwiner quantum numbers associated to the vertices, we call bulk degrees of freedom. Consider any given state. We want to ask, first of all, if we can use it to define a bulk boundary map, so a map between bulk and boundary degrees of freedom. And next, if this map is holographic in any sense. Second, we want to ask if we can consider two different portions of the boundary data, so different portions of the different subsets of boundary links. And we can use the same state to define a boundary-to-boundary map, which will be a quantum channel. So let me turn to this type of questions. Again, I will skip some of the details. Some of them will be in the slide if you want to read, but I will just go through them, emphasizing the main points only. So first we ask, do we get holographic maps from any particular subclass of quantum gravity states in these formalisms? And within this type of holographic states, can we find anything like a Ryuta-Kanayagi formula in our pre-geometric, pre-spacetime context? So we take a generic spin network state, defined as I said earlier, by starting from tensor products and then imposing a maximal entanglement across bulk links or bulk degrees of freedom. Those degrees of freedom, they will become bulk exactly because I start gluing them to across tetrahedra. And then I do the separation of the total set of degrees of freedom associated to the graph into bulk and boundary ones. Now, first, for simplicity, we consider the case in which we assign spins to our graph. So it's a quantum state with a given assignment of spins. So it's a special case, no superposition, as a starting point. So the only dynamical degrees of freedom are the intertwiner labels. When you do this, then the bulk and boundary data decouple, and the Hilbert space, in fact, can be factorized. So this is why a very special and simpler case. Now you can use the state we started from to define a map from bulk to boundary degrees of freedom. And the boundary degrees of freedom is simply given by a particular assignment of spins on the open links. And the bulk state is basically obtained by contracting the general state with the one associated to the boundary. What is left is, of course, only degrees of freedom on the boundary, on the bulk. And in fact, we can do the other way around as well. This is the case I've reported in the slide. We first define a subset of degrees of freedom in the bulk, which is intertwiner. We can sum over them with some weights. And then we contract the general state we have with this state only depending on bulk degrees of freedom to obtain a state that only depends on the boundary ones. The kernel of such a map between bulk and boundary is exactly the state we started from, the spin network state we started from, depending on all the data. Now, staying within this, in the case of a fixed assignment of spins, the factorization takes place of the Hilbert space, and we can proceed more easily. Let me just mention what is the difficulty in the other case. If you sum over spins, you do not have this factorization, so any definition of entanglement between bulk and boundary is ambiguous because there's no preferred notion of subsystem. So one way in which you can proceed, and we will say something about this later on, but we will also see an alternative strategy, is to embed the fixed spin sector into a more general Hilbert space only related to the bulk and one only relating to the boundary, which includes a sum over bulk or boundary data respectively. Then we can proceed as I did for the fixed spin case, exactly in the same way. You can proceed and then ask the same questions we will ask now in the fixed spin case. I just point out that this procedure is useful, but it's ambiguous because the very definition of the embedding space is ambiguous. Okay, so let's stay in the fixed spin case. We can ask if the map we just defined between bulk and boundary degrees of freedom is an isometry. We take this isometry condition as a sort of a proxy for what it will mean to be holographic, because it means that if it is isometric, you're preserving the scalar products, and so in a sense you're preserving the information from the boundary data to the bulk data through the map given by the quantum state. So it's a proxy. It's not a full definition of holography, of course, but it's as good as it goes at the moment. So we can define the isometric condition for the map, and this translates into a condition for the reduced bulk density matrix that you obtain from by taking the global state and tracing over boundary degrees of freedom. It turns out that the condition for this bulk density matrix is that it has to be of maximal entropy. It has to be maximally mixed. In other words, the bulk boundary map defined by the state is isometric if the bulk density matrix is maximally mixed, so it has maximal entropy. So the next task becomes to compute the entropy for this reduced density matrix. We compute the entanglement entropy is complicated, as you can imagine, so we compute something that should approximate it, hopefully, which is the second Renyi entropy. We use the standard replica trick to compute the Renyi entropy. And then here come two key steps that allow the resulting calculation to be performed. First of all, we randomize over the assignment of vertex wave functions in our quantum state. You can take it just as imposing a maximal ignorance, because we use a uniform probability measure of what is actually going on in the bulk. You can joke that we have in fact maximal ignorance also about what is going on for overall quantum gravity states, but let's try to stick to the slightly more technical points. And the second approximation is that we take the bond dimension on our links, which is basically the measured by given by the spin labels, to be large. So we work in a large spin approximation, which simplifies again a bunch of the later calculations, because it kills some of the quantum fluctuations associated to our states for a number of geometric operators. So technically, the way we do this calculation is to translate the spin system we have here, which has to do with the spin assignments on the links given by our quantum gravity state, into a different type of spin system, which is in fact an Ising model on the bulk graph. Now, this Ising model is purely a technical construction. There's no physical degree of freedom associated to the Ising spins. The spins had to do with this swapping matrix, swapping operator S that you see in the formula for the Renyi entropy. Again, skipping a lot of details, what you basically get is that the partition function the quantity that you define looks like formally a partition function for our Renyi entropy associated to the reduced density matrix for the bulk, can be written as the sum over this spin associated to the Ising model, to this artificial Ising model, weighted by the exponential of an energy for the Ising model itself. And the Ising model is spins on the bulk vertices, and then there are some fixed spins on the boundary links, which in fact have to do with the choice of state and with the initial spins we've used. So maximizing the Renyi entropy, which is maximizing the mixed nature of the bulk, reduced bulk density, corresponds to minimizing the free energy of the Ising model. You do the calculation, and the general result we find is that the lowest energy configuration, the one that gives the most isometric quantum state, meaning the type of quantum state in which through which you define maximally isometric bulk boundary map, is the one in which the spin assignments to our state, defining our state, is maximally inhomogeneous. So the more non-uniformly you assign the spins, the SU2 spins, the quantum geometric data to our quantum state, the more it defines an isometric, or if you want, holographic map. Then you can instead ask, in the same type of context, how you can define a boundary-to-boundary map, and whether you have some form of holography there. So same construction. Now, instead of defining a density matrix for the bulk tracing over degrees of freedom on the boundary, you consider two regions on the bulk in the boundary, sorry, and you trace over one of them, leaving a reduced density matrix for the complement of boundary data, and of course your map will still depend on all the bulk degrees of freedom, and therefore the details of the quantum state you started from. You perform again the same procedure. You compute the Rényi entropy, because once more you find that you have to maximize the mixed nature of the reduced density. You obtain again an effective spin system, Ising spin system, corresponding to your state, and you have to once more try to compute the Rényi entropy for the reduced density matrix through calculation of the free energy of this Ising spin or Ising spin. Now, we are still in the context of fixed spins, fixed spin assignments in our quantum state. We first can do the calculation for an homogeneous assignment. So all the spin network labels are equal. All the spins are equal. In this case, we compute the Rényi entropy for the density matrix once more, corresponding to having traced out all the complement of a boundary region and being left with the reduced density matrix for a particular subset of open links on the boundary. It turns out we do get a discrete counterpart of a Ryuta-Kanayagi area law, because the entropy tries to minimize to consider a minimal surface. So a surface that in the bulk of your quantum gravity state graph in the network in the bulk separates the two regions in that in the boundary you can associate to the two regions of the boundary you were trying to measure the correlations of. So, and the area in this context in which all the spins are the same of this minimal surface in the bulk is basically the number of links that are crossed in the bulk by the surface itself. So in the case in which the intertwiner entropy, so the quantum correlations among bulk degrees of freedom, is in fact vanishing, then you get exactly this type of Ryuta-Kanayagi area law in a combinatorial setting, in a combinatorial discrete setting. The moment you start adding intertwiner entropy, so quantum correlations between bulk degrees of freedom, leaving whatever you were doing with the boundary untouched, then you start getting bulk corrections to the Ryuta-Kanayagi area law. And you can compute in principle also the corrections coming from large amounts of intertwiner entropy. More interestingly, the moment you have an inhomogeneous assignment of spins in the bulk, and you go ahead with the same type of calculation, things become a little bit more complicated, because you have in fact an effective easy model with inhomogeneous couplings, but you can still do the calculation. You find again a Ryuta-Kanayagi area law in the same type of with the same type of procedure and with the same resulting formula. And what happens when you start adding non-zero intertwiner entropy, so bulk entropy, it's that the minimal surface in the bulk to which the area law is associated enters less and less inside the region with non-vanishing quantum correlations, internal quantum correlations. So much that when you start increasing this intertwiner entropy, in the limit, the Ryuta-Kanayagi surface just doesn't enter and defines the boundary of the bulk region with large bulk entropy. In fact, in the limit in which you are considering the boundary region you are computing the entropy for to cover the whole boundary, this basically defines the surface, the boundary of a closed bulk region. This is exactly what the Ryuta-Kanagi formula does in the limit in which it reduces to the black hole entropy. So somehow there is, it seems that an internal region that has growing and in fact maximal internal entropy behaves from the point of view of this bulk boundary correspondence, or also this boundary correspondence, in terms just like a black hole would do, at least from the point of view of the entropy. Okay, then I think I have to skip this part because I want to go to the dynamical part. Yes, Albert.
So maybe, I mean, I was planning to ask some questions at the end and maybe we have chance for discussion, but perhaps I'm not sure whether one of the message I got here was slightly confused in the sense that I understood that the moment you start having some, quantum correlations between the degrees of freedom in the bulk, you start to have this departure from the standard Ryu-Takanagi formula.
The Ryu-Takanagi formula computing entanglement across, between boundary regions, of course, across the boundary, but only looking at boundary correlations.
Yes. However, I mean, I guess that's something I was naively not expecting. I have not thought a lot about this in the sense that if I'm not mistaken, in the usual ADS-CFT context, there, you would expect that the deviation, whenever you are close to a semi-classical regime, I mean, that you have a sort of emergent, approximately classical space-time, that then you would have only small corrections to the Ryu-Takayanagi formula, right?
Yes, I think so. That's my understanding as well.
Right. And then the question is, would then, from what you're presenting here, be led to conclude that the entanglement between degrees of freedom in the bulk should be in that case rather small?
No, I think that it's that to the extent in which I can read it the other way around. I mean, that's how I understand the situation. I'm also not an expert, but my understanding is it be the other way around. To the extent in which I neglect the quantum correlations between the quantum geometric degrees of freedom in the bulk.
Yes.
So inside the black hole.
Yeah. Well,
then
although it could be a black, it could be. Sorry, it could be also a bulk without black hole, right? I mean,
it can be large, but what I'm computing here is the quantum correlations across whatever, fundamental degree of freedom would make up such an effectively classical black hole.
Yes.
So in a sense, I'm saying, yes, maybe it's counterintuitive that even a classical black hole is a highly quantum system from the point of view of the underlying quantum gravity degrees of freedom.
No, but so that I would not be surprised. That's what I was kind of expecting. That's why I was a bit surprised. I understood, and otherwise we can discuss this afterwards. That because of this point, that even if something like a large, black hole, in terms of the microscopic degrees of freedom, it should be a highly quantum, and there should be substantial entanglement. Then I would expect that you would have substantial quantum correlations in the bulk degrees of freedom. But then what I was learning from the results you were presenting here is that that would lead to substantial deviations from the Ryu-Takayanagi formula.
Well, what happens is that you do get, in a sense, the Ryu-Takayanagi formula, but now it becomes the Bekenstein-Hawking entropy, because the Ryu-Takayanagi surface, in this case, becomes the horizon surface. So in fact, what we do get is that you get a correction to the standard Ryu-Takayanagi formula until it becomes, in fact, again a measure of just area, but now the area of the horizon.
I see. So maybe we can continue the discussion at the end.
Anyway,
Thank you very much for the clarification.
Anyway, so then I'll entirely skip this last part. So the next step that I was intending to discuss briefly was the situation in which you have this superposition over spin assignments, so quantum geometry data in your state. And therefore the factorization doesn't hold anymore, and you have to resort to different methods to define something like entanglement. I mean, strictly speaking, you cannot really talk of entanglement because you don't have subsystems, and you rather talk about defining an quantum information channel from bulk to boundary, or from two different regions of the boundary. And you have to adopt a more algebraic approach, not focusing so much on the Hilbert spaces because they don't factorize, but focusing on the algebra of observables, defining the different regions you want to put in information contact, so to speak. So let me skip this part and let me now move on to illustrate one way in which you can use information theoretic structures and tools in the context of quantum gravity processes. So the dynamics of the type of states I was discussing up to now. So let me go in steps. First of all, you can describe in most of these approaches, the typical processes can be captured by two types of data. First of all, there is a combinatorial part, which can be itself described in terms of events. I mean, I put it in quotes because these are not space-time events or physical events in the usual sense, and order relations between pairs of them. So what you have is a directed graph. All the processes in these quantum gravity models can be captured using directed graphs. The moment you have Lorentzian models, so the type of quantum geometry data you have associated to these graphs admit Lorentzian discrete geometric interpretation, then you can try to also interpret the orientation, the order relations in this directed graph in a causal manner, as a sort of causal relations. But again, in the pre-geometric sense, in which, for example, you can do it in causal sets. If in particular you take these directed graphs and you impose or you find that you have no closed loops of these order relations, then you have indeed a pose set, a partially ordered set, or a causal set. Now, the quantum theory assigns to these directed graphs Hilbert spaces and operators. Now, the Hilbert spaces can be associated to the links, to the oriented links in these oriented graphs, in these directed graphs. And the elementary evolution operators are associated to nodes, which for simplicial complexes to which these directed graphs may be dual, are then 5-valent. So what you have is this type of directed graphs with an assignment of elementary evolution operators on the nodes and Hilbert spaces on the links. If the quantum states are of the type I discussed up to now, then the Hilbert spaces on the links are just the Hilbert spaces for individual tetrahedra, quantum tetrahedra. And the evolution operators are those that you will associate combinatorially to high-dimensional simplices, in particular 4 simplices in the examples I'm considering up to now. Any given quantum gravity model will give you, when defining the dynamics of your theory, will give you not only the Hilbert spaces that I discussed up to now, but a choice of elementary evolution operators for the nodes, to which you can also add some additional gluing operators for the links. And the amplitudes, the quantum transition amplitudes, you would say, in your quantum dynamical theory, will be defined by contracting or tracing over any complete basis in each link Hilbert space shared by different operators, an appropriate ordered product of evolution operators on the nodes and in case also on the links. So this is a general structure that all spin-farm models have, and a general structure that you can give also to lattice gravity path integrals when formulated with this type of quantum geometry data. And it's also the type of amplitude you get for processes in group field theories for models with the same type of quantum geometry data. So it's a very general structure for all these quantum gravity formalisms. The full dynamics for your quantum gravity model would then involve a sum over histories, or a sum over all possible such processes, weighted by the amplitudes so constructed, times some additional combinatorial factor if your dynamics includes a further dependence on the combinatorics beyond the one given implicitly in the amplitudes obtained by the tracing procedure I defined above. Now, I'm staying at the level of Hilbert spaces and operators because it's the quantum information structures that I want to emphasize. But in case you're probably wondering what does this have to do with gravity and geometry beyond what I said at the very beginning. Well, the point is that in appropriate semi-classical approximations, the amplitudes I just defined will take the form of path integrals for discrete gravity with the exponential of a discrete gravity action, say the Regge action for some models, on the simplicial lattice dual to the directed graph you started from. Okay, so in practice, you are secretly doing lattice gravity path integrals in a different type of language and using different type of dynamical variables. But that's the type of structure you have. Okay, so this is the type of dynamics you can define. As I said, this is common to both discrete gravity path integrals, spin-farm models, and you can recover a more standard description in terms of lattice gravity in appropriate approximations. Now, what do we do with this? Again, now I don't want to do quantum gravity, and I'm not interested in this context in the extraction of geometry or effective field theory and so on. I'll leave it for another talk. Let me ask a number of questions that have to do just with these quantum structures. So this is the structure I gave is also the one that defines so-called quantum causal histories, so that you interpret the elementary operators at the nodes as unitary evolution steps, and so the whole thing is a sort of a discrete causal structure you are defining. Now, is the quantum evolution defined in this by these processes, these quantum processes, unitary? Okay, you can identify what conditions you need in order for these processes to be indeed quantum causal histories, including unitary properties. What people did initially, and what is the natural thing to do once you're given this type of dynamical processes in quantum gravity, is to impose conditions on the operators and on the elementary operators, such that indeed you have unitary evolution across maximally acausal subsets. So you impose that the moment you have some maximally acausal set of link, meaning links not related by evolution operators, and you take two of them, then you use the evolution operators that relate these two different maximally acausal subsets of links, and you impose conditions on such evolution operators. They have to be reflexive, antisymmetric, transitive, and in fact unitary. If you have and this imposes a restriction on the type of elementary operators you have on the nodes. If these conditions are satisfied, then indeed you have a quantum causal history in the standard sense. One problem arises because of what I said in the previous slide. In all these quantum gravity models, what happens is that you're interested in taking superpositions over all these possible quantum geometric dynamical processes. And then this type of conditions that define a quantum causal history should be in fact applied not to the elementary operators, but to the result of summing over all processes. So again, you can take two subset of links, but now you sum over all directed graphs connecting them. And now is the new operator, which is a superposition of the operators associated to the elementary processes given before, that has to satisfy reflexivity, antisymmetry, transitivity, and possibly unitary conditions. And in fact, you can show that you can implement a lot of these conditions. There are two in particular, however. There are three that are particularly interesting. One, when you start imposing transitivity at the micro level, then this would imply that somehow the evolution between the operators defined in terms of such directed graphs is to a large extent independent of the particular directed graph you've chosen. And for a theory that is not topological, like quantum gravity in 4 dimensions, this is probably too strong. You do want a dependence on the, at least to some extent, you want a non-trivial contribution for all the allowed microprocesses. Second, the transitivity of the full evolution becomes basically the composition of probability amplitudes, and that's exactly what you would expect, and it's interesting that you get this condition from this other point of view. What is problematic is unitarity, because if you want unitarity for the evolution defined by a larger superposition of, if you want unitarity for the evolution defined by superposition over all the micro processes, then the elementary operators you associate to the nodes in the microprocesses should not be unitary. So the elementary microprocesses should not be quantum causal histories themselves, which may be intuitively reasonable, maybe, but it creates a lot of trouble because it means that if you want to constrain your definition of quantum gravity dynamics, so the type of models I've shown, the type of amplitudes I've shown earlier, by the imposition of unitarity for the global evolution, you are left with very little constraints. You can use this condition only if you can somehow control mathematically the full sum. Then we can ask a second question. Okay, in general, do we get closed time-like loops in our quantum gravity models? The answer is yes. Generically, we get them, and but this is the presence of such quantum closed time-like loops. It's a problem because again it spoils the desire to get a proper quantum causal history, and it's a bit of an issue because it also means that our elementary processes cannot be taken themselves to define a quantum circuit. So we should ask, what do we do? We have these causal loops in our quantum gravity models, and people study a little bit different strategies, and there are three main possibilities. You can do things by hand, and by hand kill the causal loops. You can simply try to define a restricted model in which they are simply not present by fiat. This is in many ways what is done, for example, in causal dynamical triangulations. And we know from causal dynamical triangulation that it does make a difference in the resulting dynamics, in particular for the reconstruction of continuum geometry. You can be a little bit more moderate and correspondingly ambitious, and just try to define quantum dynamics that suppresses the causal loops without eliminating them altogether. Or you can go a little bit more into the details of the dynamics and check under which conditions the causal loops can in fact be entirely harmless in terms of the propagation of information inside the directed graph. And okay, I'm not going into details here because I finished and I just close with a couple of final remarks. So we come from quantum gravity, as I said, and we get amplitudes associated to directed graphs with the type of structure I emphasized up to now, I discussed up to now. We can ask to what extent the models we have so far know about this possible underlying causal structure, in particular, how much they know about the ordering relations among elementary events in our directed graph. So the orientation of the graph. Now, this question can be answered in the quantum gravity models, but I want to take a step back and remind you that this question can be asked already formally at the level of general quantum gravity path integrals. Assuming I can define a quantum gravity path integral, I can write it in phase space variables, in a canonical decomposition, and in a particular gauge, I'm left with an integration over the lapse, or the proper time, if you want, elapsed from initial to final slice in a global hyperbolic manifold in which I'm defining my canonical path integral. And then it's well known that depending on how you integrate over the lapse, if you integrate only over positive proper time, or you integrate over the full infinite range for the proper time, then the resulting path integral will know or not about the space-time orientation. So the integration over the positive range only will basically erase the dependency on the orientation. Sorry, in fact, I think there is a typo here. The formula for the canonical scalar product should have the integral up to minus infinity. If you instead integrate only over positive lapse, then indeed your path integral will register the space-time orientation of your manifold. One will give you a canonical scalar product, and the other will give you what in the literature was suggested to be a causal transition amplitude. It turns out that you do the analysis in all the known models in loop quantum gravity, spin foam, group field theory literature, and you end up with a quantity, with a definition of the dynamical amplitudes that does not register the orientation of your complex, is everywhere symmetrizes over the two possible choices of orientation. In fact, already at the level of the individual links. So you can restrict and construct, you can restrict these amplitudes to register the orientation to only one of the two possible orientations everywhere with some consistency conditions, and construct a causal model. But although I was heavily interested and involved in all this, I admit that the constructions so far are entirely ad hoc. So you really do the restriction by hand. We don't have any first principles algorithm or strategy to define such causal transition amplitudes. Okay, with this I conclude. I apologize for taking a little bit longer. There are a few key points that beyond all the technical details I would like to stress. The first is in perspective, which is that from a number of considerations comes the suggestion that space, time, and gravity are in fact emergent collective notions, and that is useful to consider the universe and to treat it in our quantum gravity approaches as a sort of a quantum many-body system made out of non-spatio-temporal, pre-geometric by definition entities. More concretely, I've shown that in a variety of quantum gravity formalism, you can find the same type of combinatorial and algebraic quantum structures defining the quantum states, and they are basically quantum simplicial structures or spin networks in different concrete realizations. These quantum states can be seen as generalized tensor networks. They do show a discrete entanglement geometry correspondence in this combinatorial algebraic setting. They can be framed as information channels or quantum circuits, and you can find conditions such that when they are satisfied, you can have holographic maps for the maps defined between bulk and boundary or boundary to boundary degrees of freedom through the quantum states themselves. And this is interesting because one thing that quantum gravity approaches aim to do is to to understand what is the microscopic origin of holographic behavior we see in quantum gravity and in fact in classical gravity as well, in semi-classical gravity as well. In the same quantum gravity formulas, that's the final message, the dynamical processes take the form of spin-found models or lattice gravity path integrals, which can themselves be recast in the language of quantum causal histories. And quantum causal histories can in turn be framed as quantum circuits. So highlighting again the quantum information nature of these fundamental structures. But then, if you want to really impose all the conditions that define a proper quantum causal history and therefore a proper quantum circuit, you will need to constrain, to impose specific conditions on our quantum gravity amplitudes, which are in fact non-trivial to impose, not entirely straightforward. They don't come automatically from the constructions that have been used so far. Thank you.
Thank you, Daniele, for this interesting and very broad talk, giving us a broad perspective on these subjects and the connection with quantum information. Do we have questions? I have a few, but let's see if the audience.
You have the chair, so you should give priority to.
Exactly. Well, I should give priority to others, so that's why I'm waiting to see. Otherwise, in the meantime, I can ask some
Otherwise, you can go ahead.
questions.
Sure.
Right. So, I mean, maybe just elaborating a little bit. So I must say that I have not been following these in detail, so I'm still trying to digest a little bit all this interesting information you gave us. So just elaborating a bit on the question I asked earlier. So suppose that we are considering a case where we don't have the black hole in the bulk. We still have, could be, relatively large space-time curvature, some neutron star, whatever, but you don't have an event horizon. You don't have a black hole. And so then if I want to be close to the Ryuita-Takanagi formula, sorry, I have a bit trouble pronouncing that last name. then, it would seem to suggest that the correlations between the quantum degrees of freedom in the bulk should be small. That's the part where.
Yeah, so let me tell you the way I understand it at the moment. So what seems to be happening in my view is the following. So I'm considering correlations. Sorry, I'm being molested by my cat. And luckily didn't team with the other one. Okay, so we are considering quantum correlations across degrees of freedom underlying geometry, both in the bulk and in the boundary.
Mm-hmm.
So that's why it's very hard to translate that into the language of quantum correlations between fields moving, on top of whatever geometry you're considering.
Mm-hmm.
So that's, I think, where the mismatch between the typical calculation and what we're doing here is lying, because it seems to me that we are computing in the two cases two different type of correlations between different subset of degrees of freedom. Because ideally, I would say, okay, there would be, if I make an hypothesis or a guess of how the space-time will emerge and how the usual effective field theory picture will emerge, I would say that there will be a larger subset of these degrees of freedom that will give rise to geometry. There will be additional ones that do not concur directly into the definition of the geometry and will be left to propagate, in a sense, on top of the geometry. They will be like quasi-particles on top of a given, background fluid, something like that.
Mm-hmm.
Normally, we compute the entanglement for this additional degrees of freedom on a given geometry. Here, I'm asking what is the entanglement and the quantum correlations for the degrees of freedom forming the geometry. Now, we find, so that's the result of the calculation, that if I consider entanglement across these degrees of freedom before there is any special, emergent geometric structure, then I find the Ryu-Takayanagi formula, although again in a sort of a pre-geometric setting, because I only have this discrete combinatorial definition for what it means to have an area, what it means to have what sort of degrees of freedom I'm considering. Then indeed, the moment in the bulk I start increasing the quantum correlations in a given region in the bulk, then I start getting corrections. Now, there are two statements. Indeed, the Ryu-Takayanagi formula I started from, so the one from the point of view of quantum geometry data, becomes more and more corrected. So you deviate more and more from the typical Ryu-Takayanagi formula. But what happens is also that you create a special region. Something seems to be happening in the region with high quantum correlations, that any attempt of having quantum correlations between the two boundaries is sort of left outside that bulk region. In this sense, it seems like something like a black hole is forming from the information theoretic point of view. You don't access it anymore, and whatever you can say about the correlation between the two boundaries has to exclude that region. It cannot go through that region. Okay, now is the big step in correlating with the Ryu-Takayanagi. Then it would seem that the fundamental entropy formula you get for the correlation between the two regions indeed is not Ryu-Takayanagi. But you form the black hole. Now you can try to compute the correlation excluding the region in the bulk because that one has formed a black hole. So you treat it as now you can mimic or translate it into, okay, now we have quantum correlations on the geometry corresponding to a black hole, and I only compute the correlation between the leftover degrees of freedom. Then the expectation is that you get the standard Ryu-Takayanagi exactly because you're removing from consideration the correction coming from this region. In this sense, it's not incompatible with the usual Ryu-Takayanagi formula, and in fact reminds exactly what you get in the Ryu-Takayanagi formula for what is now the surface of the black hole as the minimal surface. So in this sense, it's exactly what you get there. The point is that there is this big gap between translating from correlations among the quantum gravity degrees of freedom to the correlation we compute for fields on a given black hole geometry. And that's the whole problem of space-time emergence. And I don't know exactly how that does, especially in this black hole case. We have results in cosmology, but that's much simpler.
Okay, thank you.
I hope it clarifies a little bit what the point is. Then
yes, I mean, I think that you explained or you gave the answer already during your talk, and now you explain it better. I'm still a little bit concerned that whenever I want to have some semi-classical space-time region, approximately semi-classical, emerging in the bulk outside the black hole, without the black hole, that this would seem to hint that there cannot be much, quantum correlations. There cannot be a lot of quantum correlations between the microscopic degrees of freedom, it would seem.
Somehow what this picture seems to hint, in case, again, the how to say, the difficulty in matching the two pictures that you mentioned is the difficulty of reconstructing an effective space-time picture from all of this. So I can only share my ignorance and a few attempts, but it's not that I know exactly how it works and what is the result. That's why your question doesn't have a straightforward answer in which, oh no, you do this calculation, this is the result.
I see.
I'm just saying that what the calculation seems to suggest is that in fact, the black hole is a system that, from the point of view of the underlying degrees of freedom, is very highly correlated. But by definition of a semi-classical description, you should be able to separate the quantum correlations that make up the geometry from the quantum correlations of whatever you have left on top of the geometry. And the usual Ryu-Takayanagi formula relates to that, while the one I'm considering refers to the other one. And that's why there is a difference between the two in the calculation, but not in what the two separately say. I think what the two separately say is compatible and in fact is partially reproduced in terms of this behavior of the minimal surface, but not in terms of the formula because it refers to different things.
I see.
Anyway, that will be my understanding at the moment.
I see. No, thank you. I mean, that helps to understand a little bit how you interpret your results. So let's see if others now have some more questions.
Otherwise, we can talk on Zoom, the two of us, at some later point.
I mean, I have another slightly related question, but I'm still waiting to see if there are some questions from the audience. So, well, maybe then I can ask this other partly related question, which is that, especially in the first part of your talk, when you were considering this entanglement, and it seemed large correlations or entanglement between the boundary, I mean the boundary, I'm not sure what I could say degrees of freedom, but that you had then and the bulk. I guess it's probably because the matching with the examples I'm a bit familiar with, let's say ADS-CFT, is maybe I'm not really interpreting the connection appropriately again. But there you would have, this dual description. You have on the boundary degrees of freedom in the bulk, and you have a translation between the two, so to speak, a connection. But there you would often consider situations where you have a pure state, let's say, in the conformal field theory, and that in principle also corresponds then to some sort of pure state in the quantum description in the bulk, which is of course a highly non-trivial one. But what I'm trying to say is that there very often one considers these situations where you have, in principle, you're in a regime where you have this duality and even maybe some emergent semi-classical space-time in the bulk, but you can have a pure state on your boundary, on your conformal field
Mhm.
theory in the boundary. Instead, the situations you were considering, it seemed that you had a large entanglement between the two. And so and the state was highly mixed then for the boundary degrees of freedom and for the bulk. So I think that probably is again that the way I'm trying to interpret or
So the
compare your
point is that
result.
the starting point is, if you want, is a state for the bulk, including some boundary component.
Mm-hmm, mm-hmm.
And it's through that I try to define a correlation. I'm asking what is the correlation between bulk and boundary degrees of freedom on this state. Now, you can consider the situation in which the state on the boundary induced by this global state is in fact pure. What I'm not sure is that it corresponds exactly to the situation we find that gives holographic behavior, the one in which you have,
Mm-hmm.
this maximally mixed reduced density matrix. Um, Well, definitely the moment we take the large approximation, the large spin approximation, as I said, we are killing a number of quantum fluctuations, but I'm not sure it's enough sufficient to reduce the boundary state, the induced boundary state to be pure. I don't think so. So, no, frankly, I'm not sure. I think we are considering a more general case, and it's the
I have the impression that probably I cannot directly try to compare again the
yeah.
two situations because in your case, you can focus on the boundary, let's say,
Mhm.
degrees of freedom, but it's still additional degrees of freedom that are, that you have the bulk, what you would call the bulk degrees of freedom, but then you also have these boundary degrees of freedom, and you're still considering a full quantum system that actually would include all of them.
Yeah,
Whereas
sure.
in the ADS-CFT picture, that's not the case. You have all the degrees of freedom just on the boundary, or in the dual description that includes the bulk with this asymptotic ADS.
Yes,
And then if you
yes.
try to have both of them at the same time, that's where I think the comparison is not
No, look, that is
one-to-one.
definitely true. What you said is definitely true the moment you relax the initial assumption of fixed spins. Because as I said, the Hilbert space doesn't even factorize. So in that case, you really have to resort to different methods because you cannot even separate into two Hilbert spaces the bulk and the boundary degrees of
Mhm.
freedom. They are really, it's not a product Hilbert space. If it's a sum, it's a direct sum of product Hilbert spaces, but you have the sum. And that's
Mhm.
why you need a bunch of different techniques. When you have a product Hilbert space, so you fix the spins in the bulk and you only have intertwined the degrees of freedom as dynamical in the bulk, then you have factorization and you can in principle just consider a pure state for the boundary data. So you can compare. What I'm saying is that it's not the case we specifically considered. I think is you can
Mhm.
take it as a further special case within the one we analyzed. And I don't think that purity is induced by any of the assumptions we imposed in the more general case. So in this sense, I don't know exactly what happens when you further say, oh, the boundary data are given in a pure state.
Mhm. Mhm.
But what you said about the necessary coupling between the two is true in the sense of a map. But okay, if there was no such map, you will just not ask what is the correspondence between bulk and boundary because you would have no way to relate them. But you can separate the subsets of degrees of freedom if the spin assignment is a given. So in this sense, the two subsets of degrees of freedom talk through the quantum state you've chosen,
Mhm.
but they can independently defined.
Okay, so
Okay.
food for thought. Thank you for
Yep.
the explanation. So do we, in the meantime, still have some Any questions that came up? Otherwise, I guess that it's almost 1 hour and a half. So then I would
Okay.
just, thank you very much for the
Thank
talk.
you. Thank you again
Uh,
for staying and listening.
and maybe just for those who are still here, just as a reminder, in August, we are not going to have a seminar because of summertime. And then in September, we plan to have to resume the seminars. We will send an announcement in due time. I don't know if there's anything else that Dennis wanted to say.
No, I will just stop the recording.